we're going to do chapter 30 on Faraday's law of induction. You see, this is the opening for the chapter. When a credit card is swiped through a card reader, the information coded in the magnetic pattern on the back of the card is transmitted to the cardholder's bank. And why does it need motion? You need to move it fast to for the card reader to read it. All right, we are going to understand this phenomenon in this chapter. Faraday's law of induction is the basis of electric guitars and electric generators. All the electricity that you get in from the walls, you know, the plugs of the wall or socket, you get from the electric generators that are somewhere outside the city are created, some power plants. They create electricity and send it to the city. And also, when in your hard disks of your computer, when the hard disk, the reader reads the information on the disk, there's a little coil inside, very, very small coil, and that goes over the magnetized regions, very small magnetized regions on this disk. And then when the disk moves, it collects the information, reads the information on the disk. Or in the new hybrid or electric cars, you probably you heard that if you brake, the braking, most of it is magnetic, and then the energy that is stored in the kinetic, in form of kinetic energy for the car, turns into electric energy and charges the battery, and then later on it can use it again. And in any motor as well, the engines, they create high voltage electricity for the spark plugs in the engine. That is also a creation of high voltage electricity. Also is done by the law of induction. So we're going to talk about the Faraday's law of induction in this chapter. So there are two different experiments here. One experiment is that when you have a coil here, or just a circular loop of wire connected to a galvanometer or ammeter, when you move a magnet in front of it, the ammeter registers some current. And so there's a current in this one, even though there's no physical contact here. Careful examination resolves these observations. A current appears only if there is relative motion between the loop and the magnet. One must move relative to the other. The current disappears when the relative motion between them stops. Faster motion produces faster current. If moving the magnet's north pole toward the loop causes, say, clockwise current, then moving the north pole away causes counterclockwise current. If you do the same thing with the south pole, the current will be reversed. The current produced in the loop is called an induced current. The work done to do this, and later on you will see that it is in fact the electric field created, is called induced EMF. And the process of producing the current and EMF is called induction. So this is the first experiment that involves motion. So if you have a magnet, you have to move it relative to the loop in order to create a current in there. But here's another type of experiment that doesn't involve any motion. An ammeter registers the current in the left-hand wire loop just as switch S is closed to turn on the current in the right-hand loop. So you see, there's no physical contact here. This circuit is completely separate from this circuit. But when you close the switch, the current starts to flow in this circuit, and that creates a current in the other circuit, even though there's no motion. Or and if you keep the switch closed, this current stops. It starts for a little bit while this current is increasing until it gets to the maximum, and then there's no current in here. And then when you open the switch, this current dies suddenly, then there's another current in here. So if you close it and open it, then during the closure or opening, it creates a current in the other one. So no motion is involved here. We get an induced current and thus an induced EMF only when the current in the right-hand loop is changing, either turning on or turning off, and not when it is constant, even if it is large. If no matter how large the current in here is, it doesn't create any current in here. Only it creates a current here if it changes. The induced EMF and induced current in these experiments are apparently caused when something changes. But what is that something? Faraday figured this out. That's why we study this law named after Faraday. All right, any questions so far? All right, these are done by one loop. Of course, this effect is very small, and this is just hypothetical and it's ideal case. But more realistic experiments can be done in any lab. We have these kind of coils or solenoids in the lab, and magnets. If you connect the two sides of this wire that is wound many turns with the galvanometer here, if you have a magnet, if the magnet doesn't move, then it doesn't create any current in this coil. But if the magnet moves, it creates some current. And instead of the magnet, as I mentioned, this coil exactly works like a magnet. And if that is connected to a battery so that there's current going into this, that also works like a magnet. So you can move this up and down, and that creates a current in the secondary, even though there is no physical contact in here or electrical contact between these two circuits. You can also put this inside the other coil. Again, there's no electric contact between them. And then you turn this switch on, close or open. Therefore, the current in this one, the first one, increases or dies out. Then that increase or dying out creates a current in here. When the current is on and it is constant, there is no current created in this way. So only the change creates the current in the second one. The change is very important. So all of these induce a current in the coil. And the question is, what do they have in common? They cause the magnetic field through the coil to change. All right, but what exactly, how much magnetic field? All right, that leads us to define a magnetic flux. Remember, as we define the electric flux through a surface, we can also define a magnetic flux. If we have a dA here, so we have a surface of area A, but it is not a flat surface, and it is in a magnetic field that's not constant. We want to see how much magnetic field passes through this surface. We divide it into a small areas, dA, and we define an area vector dA perpendicular to the surface at that point that has a magnitude the same as dA, So this dA is the magnitude of this area vector dA. And this is the magnetic field. We calculate the perpendicular component of magnetic field to the surface or parallel to the dA vector. And we multiply the dA times that perpendicular component. So you can write that as B dot dA. That is the flux, small flux passing through this area. And then if you integrate over the whole surface, you get the total flux. So that B dot dA is B perpendicular dA, or B times dA times cosine phi. So that gives us a small piece of this flux. And then if you add all the contributions everywhere on the surface, you get the total flux. So magnetic flux is defined as phi of B as integral of B dot dA. So that's very similar to what we had about electric field or electric flux. We call it phi E. Now we call this one phi B. And the unit of that is Weber, which is 1 Tesla meter square. Unit of B is Tesla meter. Unit of area is meter squared. So this becomes Tesla meter squared. And if in a special case when B is perpendicular to the area and area is flat and B is uniform, phi is just B times A. Any other case, you have to do this integration. All right. Any questions? So this is similar to electric flux that we had. Now we have magnetic flux. So what is Faraday's law now? Faraday's law says that the change of magnetic flux in a loop, in a coil, creates the EMF in that coil. So the EMF, which is denoted with this curly E, is equal to negative rate of change of flux of B through that device. Okay. If the magnetic flux phi B through an area bounded by a closed conducting loop changes with time, a current and an EMF are produced in the loop. This process is called induction. The induced EMF is given by this formula. And usually we have more than one loop. If the loop is replaced by a closely packed loop of a coil of n turns, the induced EMF is n times bigger because each one creates an EMF and all of them are in series. So the EMF becomes n times d phi over dt. And there's a negative sign here. What is that negative sign? That negative sign indicates the direction of the induced current or induced EMF. And it follows the Lenz law. That negative sign is actually the indication of the Lenz law. An induced current has a direction such that the magnetic field due to the induced current opposes the change in the magnetic flux that induces the current. So basically, whatever creates that current is created in a direction to oppose the original change in the magnetic flux or magnetic field. So induced EMF and induced current have the same direction. Here are some examples here. Let's say you have this loop of wire and there is a magnetic field that is downward and is increasing. The external field is B and it is increasing, and that's the downward, okay? So according to Lenz law, says that the current is created in a way that the magnetic field of that current, induced current, which we call B induced, which is due to this induced current, opposes this magnetic field that is increasing in this direction. So increases in downward direction, this current creates a B field upward to oppose that. All right. So this is the key. Whenever you want to find the direction of current, in a loop, when magnetic field changes inside the loop or magnetic flux changes inside the loop, you need to use this rule. Say, which direction is it? Is it increasing or decreasing? If it is increasing, the magnetic field of the induced current opposes that. And then you use right-hand rule, as you see in the figure. You put 4 fingers in the direction of the direction of the current in the loop, and your thumb is in the direction of induced B field. Or when you know this one is going down and increasing, you know that this B field is opposing that. And then you can put your thumb in that direction, and your 4 fingers shows which direction the current is in the loop. This is another example. Now external field B is decreasing. The field is downward and it is decreasing. If it is decreasing, Lenz's law says that the induced B field or B field of the induced current will support that because it is decreasing. All right, it doesn't want to change. So it supports that. And then you know which direction the B field of induced current is. Then you put your thumb in that direction, and then your 4 fingers of the right hand shows which direction the current will be. All right, so the current will be in this direction. This side is away from you. Be careful when you look at this, it could be misleading. This side is away from you, this side is close to you. Okay, that's why you see this side is behind the page. It is a little bit lighter than this side. Okay, so when the B field is reduced, the external magnetic field or magnetic flux is reduced, the induced current creates a magnetic field that supports it. So then you can find which direction the induced current should be. And then in this case, you have the external field increasing, but it is upward. The external field is upward, increasing. If it is increasing, the induced current creates a magnetic field to oppose that, oppose the increasing magnetic field. So again, B induced will be opposing that, so it is downward. And then you put your thumb in the downward direction, your 4 fingers shows the direction of the induced current in the loop. And in this case, the external field is upward and decreasing. This B is upward and this is the external, right? So it is decreasing. So Lenz's law says that the induced current creates a magnetic field that supports it. So you know which direction the B field should be to support that. And then you put your thumb in that direction, your 4 fingers show which direction the induced current is. Is it clear? Any questions?
So in short, whenever there's a decreasing field, it will always be in the same direction rather than opposite of it.
Yes, decreasing means that B field of the induced current is the same direction as external B field, yes. So this is what was the next thing to say. In other words, the induced current is in a direction such that its own magnetic field or flux opposes the external field if it is increasing, and supports the external field if it is decreasing. All right, so it is in the same direction if it is decreasing. It is opposite direction if it is increasing. Okay. All right. In fact, you don't have to have a wire in space in that region to have the EMF. An EMF is induced by a changing magnetic flux, even if the loop through which the flux is changing is not a physical conductor, but an imaginary line. The changing magnetic field induces an electric field E, and every point of such a loop, at every point of such a loop, the induced EMF is related to E by this formula. Remember, it is integral of E dot ds. This was the potential, right? But here we don't call it a potential, call it EMF for the technical reasons. Okay, so this is the same as potential. This is what creates the current in the loop, if there was a loop there. But there's creates an electric field. The change in the magnetic field creates an electric field. And this is the complete form of Faraday's law that says that this EMF, which is integral E dot ds, equals to negative rate of change of flux of magnetic field. This is, in fact, the integral form of Faraday's law. You can turn it into differential form, which is, of course, beyond the scope of mathematics in this course. But that is the complete form of Faraday's law. Okay. Any questions? So you see that here, the magnetic field is into the page, and now into the page, if it is increasing, means that the induced current, if there was a loop in here, induced current would oppose that, means the induced current creates a B field of its own that is out of the page, because this B field is into the page and it's increasing. So you use your right hand rule. If you put your thumb in the direction out of the page, you see that your 4 fingers shows the counterclockwise direction, which is this current as is shown here. But it doesn't have to be like that. It creates an electric field in that direction, right? And doesn't have to be a conductor here. This is a copper ring in here. This is just a line, imaginary line. So Faraday's law says that if there is a flux changing, there is electric field that's circulating around. And it is the same for electric field. If the electric field changes, the magnetic field will be produced the same way. We're going to talk about that in chapter 31, 32. All right. So we have motional EMF. What does that mean? Means that if you have a rod and it moves in a magnetic field, this is a magnetic field into the page, see, it crosses. This is magnetic field in this region, and this rod is perpendicular to the magnetic field, is moving this way. When it is moving, of course, this rod has all electrons and protons in it. So it means that the charges inside the rod are moving. Let's suppose that there is a positive charge here. Of course, the electrons will move, but we talk about positive charge, this will be exactly the same as negative charge. So when this charge is moving this way, remember that there is a magnetic force acting on it. So F of magnetic field, right? Which is Q V cross B. If you imagine V cross B, turn your 4 fingers of your right hand from right into the page, you see your thumb shows up. And because Q is positive, that is the direction of magnetic field, magnetic force acting on this charge. All right, so the charges, positive charges tend to come this way and negative charges tend to go the other way, okay? In this case, electrons, if it is a metal, electrons move a little bit downward because of this magnetic force, which is downward for electrons. And then here will be an accumulation of positive charges and accumulation of negative charges on this side. And these positive and negative charges create their own electric field, and the electric field also will be in the downward direction and applies a force downward on the positive charge. So because this side becomes positive, you can imagine if this side becomes positive, this is positive charge, so it will be repelled this way. So these charges separate until when these two forces become equal. And then when these two forces become equal, E should be equal to VB, the same as velocity selector, remember? So E equals V times B. All right. So there's electric field like that and created. And now we have this relation. And then what is the potential between these 2 points, potential between A and B? We say the potential, magnitude of the potential is E times the L, integral E dot dl. E is constant here because V is the same for all of them and B is the same. So E comes out, becomes integral dl, becomes L. So if you multiply by L, you get V, the potential between A and B. And then that's equal to E times L. And if you multiply that by L, it becomes VBL. Okay. So this EMF, motional EMF, is VB times L. So this is one way to look at this phenomenon. Another way to look at this is that you can consider this to be part of a circuit like this in here. So you see, this is the same rod, but it is on a rail that is connected like that. And that part is stationary. And when you move this, this is in contact, so that we have a loop of wire basically that changes. One of the sides is moving. And this motion creates an EMF, and you can use the Faraday's law to calculate EMF here. So Faraday's law says that E equals to d phi dt, rate of change of phi. Of course, the negative sign is not shown because we're just looking at the magnitude here. Is rate of change of flux of magnetic field through this loop. And you see that everything is constant. The only thing that changes here is the area. The B field is the same, but the area changes. So let's quantify that. So the magnetic field, magnetic flux is a magnetic field times the area, because the field is constant and uniform, and the area is perpendicular to the B field, as the special case we talked about. It happens here. So flux is equal to B times A. And so it becomes rate of change of BA over T with respect to time. But B is constant, so you can take B outside this derivative. So it becomes B times dA dt. But the area of this can be written as the length times this x, but the length is constant. So L times the x is the area, but L is constant, comes out again. So it becomes BL times dx dt, right? And what is dx dt? It means rate of change of this x from here to here becomes the speed, right? Or velocity of the rod. So it becomes, EMF becomes BLV. So you see that you can look at it this way. Let's say that, okay, the motion of the charges create an EMF on between the two sides of this rod, or we can say, okay, that is like an imaginary circuit here that changes magnetic flux in it. So again, it creates the same EMF, which is BLV. All right. Any questions? So that's called motional EMF. Now, what is inductance or inductor? An inductor is a device that when you have current in it, it creates a magnetic field, and the magnetic field creates a flux inside the winding of itself. All right. And when there is n turns, you see that flux on each one is phi, and you have n turns, and then becomes n times that. So the inductance of that inductor is defined to be the total flux divided by the current in it that caused this flux. So this is the definition of inductance, L. And the unit of inductance is called Henry. And 1 Henry, which is denoted by capital H, is 1 Tesla meter squared over amp. You see, this N is dimensionless, but phi is Tesla meter squared or Weber divided by amp, right? And you can apply this formula for a solenoid and calculate this. Let me show you how this comes in. I don't have it here, so assume, imagine there's a solenoid that has n. It's like this. It has n windings per unit length. Usually you have n. You have total total number of windings, and it has a length L, right? So what is the magnetic field inside when we have N? So for an ideal solenoid, we found that the magnetic field inside is mu naught N times I, right? N was the number of turns per unit length, and I was the, we use lowercase I here, doesn't matter. Mu naught Ni is the magnetic field. So if you take the length L of this ideal solenoid, it has N times L windings, because N is the number of turns per unit length. So the number of windings in the length L of this becomes L times N. So the flux, the total flux phi, becomes N times area times B, right? But then the N is lowercase n times L, so N times L, and then area, and then B is mu naught N times I. So phi B is that, right? For the length L of that solenoid. And then we want to find L. L is equal to phi N. I mean, N is already there, so this is N phi B. Let me say phi B is B times A for one round, but this is N of them. N phi B divided by I. So it means that you cancel this I, becomes N, there's N here and N here, N squared A mu naught, and times L, times A's are there, times L. All right, don't confuse this L with that L. This is the inductance, that L is the length, and inductance per unit length. So L, if you divide by L, inductance per unit L is equal to mu naught N squared A, which is this formula. All right, so this is pretty much the only geometry for which we can calculate exactly what the flux of magnetic field is and what the inductance is. But for any device, there is some inductance. Usually you can measure it experimentally. All right, any questions? All right, but what is self-inductance? Suppose we have this inductor. When you send current through it, you can have current, and when there's current, there's magnetic field going through it, and it has an inductance that we can calculate theoretically. And what happens if this current changes? As long as the current doesn't change, nothing happens. Okay, the current just there's a potential difference here. It creates a current, and current goes, and nothing happens. But what if the current changes? If the current changes, then the magnetic field changes. The magnetic field changes causes the magnetic flux to change. The magnetic flux that changes causes an induced EMF inside the inductor. All right. The induced EMF is given by this. It is proportional to the inductance. And it's proportional to rate of change of the current inside the inductance. And there's negative sign because it says that the induced EMF on side of the inductor, induced EL, is opposite to the rate of change of current in which direction it is. Okay, so it creates its own current that opposes the change of this original current. All right. So the direction of EL, if a current I in a coil changes with time, an EMF is induced in the coil. This self-induced EMF is EL equal to negative L times di dt. Means basically it's proportional to the L. The direction of EL is found from Lenz's law. The self-induced EMF acts to oppose the change that produces it. All right. So now, if you have a circuit that has an inductor in it, you see what happens. It's like this. You have a battery, and you have a resistor, and you have inductor. Okay, and normally, if this was just a simple wire, when you connect this to A, suddenly there's a current, right? Current goes from 0 to maximum very, very fast. But this inductor doesn't like that. When the current wants to change from 0 to maximum, this produces a EL in the opposite direction. So you see that voltage, original voltage is this way. This one creates a inductance in the opposite direction. And you can calculate, there's no room here. I just wanted to mention this, that you can calculate, and the same way as I did for the RC circuit, this is called RL circuit. You find the current as E over R, which is the maximum current, times 1 minus e to the t over tau L. And tau L comes from this equation, this formula, L over R. All right. And then when the current is going, you switch it back to B. This resistor, the inductor wants to keep the current going, but resistor wants to stop the current. So the current stops by this formula, I equal to I naught e to the negative t over tau. All right. Okay, so this is our L circuit, very similar to RC circuit. Over there, we had Q equal to maximum Q times 1 minus e to the negative t over tau. Here we have current. So the current starts from 0, goes to maximum like this. And then when you switch it back, it goes from here, goes to 0 like that. So if you already have a current, then it goes to 0 like this when there's no EMF, there's no battery in the circuit. So this is our L circuit. I don't want to spend too much time on it because it's very similar to RC circuit. And then magnetic energy. So where does this magnetic energy come from? When you have the EL like this, and you create a current, this EL becomes, I don't remember. This is the energy. Energy is U is equal to E times the charge in Q, electric EL times Q. Q is di dt, right? So Q is, oh, I don't know how to, yeah, I need to think about it. And now that I'm on this spot, I don't know how to do that. I need to think about it. 1/2. All right, let me see, what is the formula here? E times I, yeah. So you see, U is E times the power is equal to EL times I. And power is U over du over dt. Du over dt is equal to ELI. And then U becomes ELI, du becomes ELI dt. And then du, U becomes integral of du and becomes integral of ELI dt. And then EL becomes, U becomes integral of EL, which is I L di dt. Again, I use capital I di dt times I dt. So it becomes integral of L, this dt cancels, I di, and then integral of Li becomes 1/2 Li squared. All right, so the U means the energy of magnetic field inside the inductor becomes 1/2 Li squared. And now consider an ideal solenoid. An ideal solenoid like this, let's say length L of a solenoid, and has this cross-sectional area A, and has the n winding per per unit length n, and it has a current I in it, current I capital, let's say. All right, how much energy is there? We say the energy U of B is equal to 1/2 Li squared. And then we said that L was, this is the total current. L, remember, L, we had L over L equal to mu naught n squared area times area. So L becomes mu naught n squared area times L. So it becomes 1/2 mu naught n squared area times L times I squared. So that is this part is L, and then times I squared. And now UB becomes 1/2. I multiply this by mu naught and divide by mu naught. So it becomes 1/2 mu naught. Then we have mu naught squared, n squared, I squared, times A times L, right? So this is the total energy of this solenoid in per unit length, in the length L of that. What is this A times L? This area times L. What do you think that is?
Wait, can you repeat the question?
What is A times L physically? Yeah.
So-
Can say volume. It's a volume of this cylinder, right? And this is the total energy in that volume. So if we define energy, magnetic energy, energy density of magnetic field, energy density, let's say just energy density, U, let's call it lowercase u for B, equal to UB divided by volume, which is AL. That becomes 1/2 mu naught times mu naught squared, n squared, I squared. And then I can write this as mu naught Ni squared. What is mu naught Ni? Mu naught Ni was the magnetic field inside. Remember, mu naught Ni was the strength of or intensity of the magnetic field inside. So this UB means energy density inside is 1/2 mu naught times B squared. And this is the similar to what we found for the electric energy, equal to 1/2 epsilon naught E squared. So when you have electric field in space, you have electric energy density. When you have magnetic field in space, you have magnetic energy density. So magnetic energy density is given by this formula. This is the derivation of this formula. All right. Any questions? All right. So that is pretty much everything that you need to know in this chapter. And then from now, we can do some problems, some example problems. Here is one of the problems from the book. It says the figure shows 3 situations in which a wire loop lies parallel partially in a magnetic field. The magnitude of the field is either increasing or decreasing as indicated. Here it says increasing, decreasing. In each situation, a battery is part of the loop. In which situation are the induced EMF and the battery EMF in the same direction along the loop? For example, what about A? Is the induced EMF is the same direction as the EMF of the battery or in the opposite direction? So here you see B is out of the page because it's showing by a dot, right? This one B is into the page. This is out of the page. This is out of the page, right? So B is out of the page and it is increasing. So which direction is the induced current in part A? Is it clockwise or counterclockwise? What do you think?
Would it be clockwise since the field is opposite, right? So if I'm using the right-hand rule
Uh-huh.
and it's going basically being increasing right now at A is going into the page. So if the other direction would be out of the page, right? So if I'm taking it like that, then wouldn't basically have my hands basically curl.
So say that again.
So isn't it basically, well, I'm trying to look at this correctly.
Mhm.
So this current field, it's increasing. So that's going to be opposite. So
Yeah. So for this, what is the direction of B induced?
it would be the opposite side. So out of the page, right?
This is out of the page,
Oh, sorry. So into the page. Sorry.
into the page, yeah. So B induced is into the page, okay? And then,
If it's into the page, then it would be clockwise, right? Since
yeah, then you put your thumb into the page. All right. Your thumb into the page, then your four fingers show which direction? Clockwise. I can write because I don't have a lot of room. Clockwise. So induced current is clockwise, means this way. And induced current is in the same direction as induced EMF, right? So induced EMF is clockwise. This EMF is counterclockwise, right? This EMF is counterclockwise. Induced EMF is clockwise. So they are in opposite direction. Make sense, anybody? All right, so that's for that one. For B, now B field is into the page and it is decreasing, right? B induced is which way? Because this is decreasing, this wants to support it. So it is also into the page. So thumb into the page.
it would also be clockwise, right?
Yeah. So for fingers, so E induced or I induced is clockwise. But in this case, the EMF is also of the battery is also clockwise, right? So this is I induced clockwise. This is also clockwise, so they are in the same direction. What about this one?
It would be counterclockwise, right? Since it's decreasing, but it's out of the page. So
That's right. It's out of the page. So B induced is supporting it because it's decreasing. So it will be out of the page. You thumb out of the page. Your I induced is counterclockwise. Your four fingers show counterclockwise. And also E induced is counterclockwise. And this one is clockwise, so they oppose each other. Make sense? So you have to go through these steps. These, in which direction B is, and in which is it increasing or decreasing, and then induced B opposes that or supports it depending on whether it is increasing or decreasing. And then from there, you use right-hand rule to figure out which direction the induced current or induced EMF should be. Okay. Any questions? All right. This is another question, which is an interesting question. Figure gives 4 situations in which we pull rectangular wire loops out of identical magnetic fields directed into the page. All of them are into the page, the same magnitude, okay? At the same constant speed. So all of these speeds are also the same. The loops have edge lengths of either L or 2L as shown. Rank the situations according to A, the magnitude of the force required of us to do that motion, the rate at which energy is transferred from us to thermal energy, and the loop greatest of the loop, sorry, thermal energy of the loop. So how do we approach that? The loop have edge lengths L or 2L. Rank situations according to the magnitude of the force required of us and the rate at which energy is transferred from us to thermal energy. How do we, what can we say? It will be a lot of steps. So any ideas? So remember, there's a EMF for each one of these, right? Remember motional EMF? Motional EMF is what?
Isn't it magnetic field times the inductance over the area, the rate of change of area?
Not inductance. The L in this formula was not the inductance, it was
Or the length.
Yeah. BLV, right? L was the part that is perpendicular perpendicular to the direction of motion, right? Because you see, this is the area that is changing, right? So these do not create any EMF. The area is changing because of this is moving, this part is moving. The area here is changing because this part is moving, and this part is moving, and this part is moving. So you see the L that is moving, here L is equal to, here it says L or 2L. L equal to 2L for this one, L equal to 2L for this one, and L equal to L for this one, and L equal to L. This is the part that is moving. So EMF is, B is the same, V is the same. So the only difference is this. So EMF of these is equal to 2BLV. This is 2BLV, and this is BLV, and this is BLV. This is EMF that is produced. Okay, which one, how much current is produced? What dictates the current? So the current, I is equal to what? EMF that's produced divided by the resistance, right? Do they have the same resistance? So why do they have the same resistance? this is this one has the same resistance as this one. They are made of the same wire, right? So if they have the same wire, remember the same cross section, the same material, the resistance was rho L over A, right? Rho is the same, A is the same, but they have different lengths. In this case, let me call this also the length here. So what is the length of this total length? This is L, the 2L, and L, and 2L. How much is the total length? It's 6L. What about this one? The 2,
8.
8L. The other one,
6 L's, right?
6L, and
This is 4L.
4L. So you see, the larger one, number 2, has more resistance because it is more, and the length is more, right? Larger length. So the resistance, if you wish, you can call this proportional to, let me call this a unit of rho is some number n times rho L over A, and for each one of these is 6 or 8 or 6 or 4. So the resistance here, let me call this n times R. R here becomes 6R, here becomes 8R, here's 6R, and 4R, right? And then what is the current? The current becomes E over R. The current, which is E over R, we can write for the first one will be 2 over 6 of BLV over R. For the next one will be 2 over 8. And then will be 1 over 6. For the next one will be 1 over 4. Right, the currents are different. All right. Now, where does the force come from? Why do we need to apply force? You see, which direction is the induced current? You see, the B field is into the page and it is decreasing for all of them. So the induced current wants to support that. So the induced magnetic field is into the page. And if you put your thumb in that direction, you see that the currents are all in this direction, in clockwise direction. So in here, the current is up for all of them. So current is up here, and up here. So when there's current in here and it is in the magnetic field, what is the force, magnetic force on the current? So force on the current is ILB, remember? And here there is L again is 2L, here 2L, and L and L. So the forces are different, and because of I is different and L is different. So ILB becomes 2/6, right? For I times and 2, and then here becomes 2/8 times 2. This becomes 1/6 times 1. The other one becomes 1/4 times times 1. So the forces are like this, like 4/6 and 4/8, which is 1/2. And this one becomes 1/6. This one becomes 1/4. Of course, they all have the same factor. It cancels. All right, so you can make all of them the common denominator, the same denominator, to be able to compare. If you want the same denominator, what is the common denominator here? Common denominator is 12, right? So you can say this is 8/12. This becomes 6/12. This becomes 2/12. This becomes 3/12. And now the ranking is clear. So the ranking is 1 is the greatest. F1 is the greatest. Then F2. Then F4. Then F3. Right, there's a lot to be done here. So you have to figure out their EMF, and then their resistance, then their current, and then their force. All right. Any questions? In this figure, a long straight wire with current I passes without touching this long straight. It's referring to this one, is not touching the loops. Okay. 3 rectangular wire loops with edge length L, 1/2 L, and 2L. The loops are widely spaced so that they don't affect each other. Loop 1 and 3 are symmetric about the long wire. Rank the loops according to the size of the current induced in them. If the current I is constant, B, if increasing, greatest first. What do you think? If the current I is constant, let's focus on A. If the current I is constant, how do you rank the 3 loops according to the current created in them because of this current, because of magnetic field of this current? Any ideas? So this current creates magnetic field, right? If you want to find out which direction it is, you put your thumb in that direction. According to what we had in the last chapter, you put your thumb to the right, your 4 fingers show that the magnetic fields coming out above the wire and going into the page below the wire. All right. All right, now the current is constant. Is the magnetic field changing? So for A, I is constant. Therefore, B of that is constant. So therefore, flux of B is constant. Therefore, the EMF is equal to d phi b over dt. What is that? If phi is constant, what is the derivative?
Isn't it just area over T? Or
The flux is constant. What is its rate of change?
0.
Yes, it's 0. Yes. So because the flux is constant, for each one of them, the flux is not changing. Therefore, the EMF in them is 0. Okay. And therefore, of course, EMF is 0 means current is 0. Right? So all currents are, or induced current are 0. So they all tie. Okay. That's the ranking for part A. What about if the current is increasing? What can you say about that? Remember, this magnetic field is at distance r. B is mu naught I over 2 pi r. Remember, this was magnetic field of a wire. So now means that the closer you are, the larger the magnetic field, the farther you go, the smaller magnetic field. But also it is coming out in here and going in here. So what is the total flux in 3?
0, right?
Yeah, again here, there's more on each side, but they're symmetrical. So the total flux on 1 and 3 is 0 and doesn't change. Doesn't matter how much the magnetic field is. The flux is 0 because comes out above the wire, goes into the page below the wire. So the total flux is 0. But for this one, there's smaller amount of flux going in than going out. So there's a net flux here, non-zero net flux. Here is 0 net flux. Here, 0 net flux. Right? So if it is 0 and doesn't change, therefore EMF is 0. So E equals 0, E equal to 0, E is non-zero. So what is the ranking? In part B, the I2 is greater than I1, which is equal to I3, equal to 0. All right, because the second one, on the second, when the current is increasing, there is some change of flux because there is net flux, and flux is proportional to the magnetic field. So it changes. But the other ones are 0. No matter how much flux you have, how much magnetic field you have, the flux is 0. All right. Okay, that's all the time we have today. I stop here. We continue next week on Monday from here. All right.
Okay. See you, Professor.
See you.